Okay, so let's speak a little bit about, or talk a little bit about how to design DFAs, how to build them. So usually you're given a description of a language in words, right? And you really want to think about writing a program that recognizes this language. But the trick is that you want to really think about what's the minimum amount of information you need to know at any given point in time as you read the input to recognize this language, right? And the DFA would essentially be just the space of states that you need for this task, and then once you recognize what the states are, what is really the minimum information you need, usually describing the DFA is quite easy because you describe the states, then you describe the transitions, and you're done essentially, right? You need to define the starting state and so on, but the rest is relatively easy, right? And the way to think about state is that states are your memory, right? So the state itself can encode some information about what happened in the past, right? Which is, I guess, true of all of us. That's what memory is. But you want to capture what you need, but not more than that, because if you remember too much, then you're creating a large state space, and it can become quite inefficient. Okay, so let's see some examples. So let's start from the easiest thing. We want to build a DFA for the language, the empty language, right? We don't recognize any thing, so we just build an automata with a start state Q0, and let's assume the alphabet is 0, 1, so the transition is into itself, right? So it's just a hell state where everything stays where they are and you accept nothing. The second example is, of course, where the language is everything. This is also easier, right? Sigma star, because you just take Q0, you make it into an accepting state, and 0, 1 stays in this state. So this is this language. The other one is the language that accepts this one, where you accept only the empty string. So you have Q0. It's the start state and it accepts. But whatever input you get, you move to a new state Q1. And Q1 is, again, a hell state. Maybe the most interesting example of those three is the language that contains only the string 0. So we have Q0, right? Which means we didn't see anything yet. If we get 1, we go to a hell state. Right, so we put Q1. By the way, when you draw the automatas, it's not always necessary to label the state, but it's usually easier to label them so that you can talk about what's going on. So this is if you get 1, and if you get 0, you should accept. So we're going to have an accept state. Let's call it Q2, I guess. Right, and from Q2, what happened is that whatever we get, we go back to, well, not back, but we go to hell, the hell state, and stay there. And so this is the language 0, right? So far, those examples are pretty easy. So let's do a more interesting example. We want all the strings such that the length of the string is divisible by 5, right? So clearly, all we need to remember, we want to count the length of the string, but we don't really care about the length of the string. We just care about the length of the string modulo 5, right? So we just need to have states that captures this, right? So Q0, this will be the start state, and it says the modulo of the length we saw so far is 0, right? So it's a start accepting state, and then if I get 0 or 1, right, the string increases by 1, the modulo, right, here I'm using the fact that 5 times I plus 1, modulo 5 is 1, right? Remind you, modulo is just the remainder of the dividing by this number. So this is going to go to, I'm just going to write it as 1, right, to make things easier, right? Okay, from 1, again, I get 0, 1, I'm going to go to state 2. From state 2, I get 0, 1, I'm going to go to state 3, and from state 3, which means the length of the string is 3 modulo 5, and here I go to state 4, right? Now, the important thing is that if I get 0, 1 at state 4, ta-da, I go back all the way to the starting state 0. Right, this is 0, 1. So this is the automata for this language, and all we really did, we counted the length of the string modulo 5. And every state just encoded in its name the value of the counter so far modulo 5. So that was easy. Okay. Now we start with some languages that require a little bit more cleverness. So we want all the strings that ends with 0, 1, right? Now, so what's going on? In the beginning, we know nothing, right? Let's call it. Let me in fact write it as, I'm going to use some bizarre notation. I'm going to use epsilon to say, in the beginning, we saw empty string, right? And now let's think about what's happening. We can think about it as a binary tree. I see a 0, right? And after seeing 0, I either see 0 or 1, right? Now, if I got to 0, 1, this is 0, 1, this is an accepting state, right? If I started from empty string and I got here, then I'm very happy. Okay, similarly, if I got, this is this state 0, and this is going to be the state 0, 0. This is not necessarily the easiest comparison, minimal construction as far as state, but I hope that it's the cleanest as far as understanding of what's going on, right? So really, if you look on the names I gave to my states, all they do, they remember the last 2 characters we had seen. Right? So for example, if I'm on the state 0, 0, and I got 1, I move to 0, 1, right? Because the last 2 characters I saw were 0, 1. This is if I get the letter 1. Now, if I get the letter 0, I stay where I am, right? The last 2 characters were 0. So again, the name of the state encodes the last character I've seen. The last 1 or last 2, right? Depending on where I am. Okay, if I'm 0, 1, and I got a 0, then I go to 1, 0, right? And if I get a 1, I go to 1, 1, right? Because I saw 1. Okay, now, if I'm at 1, 0, and I see 0, 0, then I go to 0, 0. This is 0. And if I see 1, I go to 0, 1. Okay. Now, if I'm at 1, 1 and I see a 0, I go to 1, 0. The last 2 characters are 1, 0. This is if I see 0. And if I get 1, I stay where I am. Okay? So this is this automata, right? And it clearly, the construction is clearly correct because this automata really just remember the last 2 characters that we saw of the input. And as such, it accepts only if we're in state 0, 1. And that's it. Right. Now, I hope that you get out of this example the importance of giving meaningful names to your states. Right. The names should encode the information that you care about. Right. Now, formally, usually, if I write all this stuff formally, I would not write 0, 1 for the name of the state. I would write Q 0, 1, but that doesn't matter. Right. That's not the important bits. Okay, let's do the next example. Okay, W contains 0, 0, 1 as a substring. Okay, so this is going to be exactly the same idea as before, right? Except that we're going to be a bit slightly different. Right? So we have a start state, right, which is epsilon. And now let's just build the part that we care about, right? Let's assume that we get 0, 0, 1. So this is going to be 0, 0, this is 0, 0, and we get a 1, right? So once, if we got 0, 0, 1, we got to the state 0, 0, 1. We had seen as 0, 0, 1, and we don't care what the rest of the string is, so we have 0, 1. Okay. Now the interesting thing is, what do we do if we get some other string inputs, right? All the states are not well defined. So for the time being, we don't really need to think more carefully, because we could just write down the the binary string of what the input we saw so far, as we did in the previous example, right? So this is 1, 0. This is 1, 1. I guess here I need to have also, let me do this, it's a bit breaking up, but this is 0, 1, right? So now we have all the 4 states corresponding to seeing 2 input characters. And now we need to decide what we do, right? So the important observation is that we really need to remember only the last 2 letters. As long as we didn't get to the accepting state, in this case it's heaven, because we go there and we state the good place. So as long as we are not in the good place, all we need to remember is the last 2 letters of the input, right? So we're going to have the same transition we had before, right? 0, 1. If we get a 0, goes here. If we get the right, this was if we get a 0. If we get 1, we go here, right, and so on and so forth, right? So if we get the 1, we go to 0, 1 from this state. If we get a 0, we stay where we are, right? 1, 0, if we get a 0, we go to this state. I know it's a mess, but it's the principle of the thing, not necessarily the low-level detail. If we get a 1, we go back here, right? And finally, if we get 1, 1, we get 1, we stay here. And if we get 0, we go back to 1, 0. And this is it, right? Essentially, to get to 0, 0, 1, it must be that the last 2 characters we see is 0, 0, right? We must have seen 0, 0 in the last 2 characters, and then we get the 1. And the rest is just a mechanism to remember the last 2 characters until this good event happens. So that's the solution for this. Okay, this is going to be, doubly contain either 0, 0, 1 or 0, 1, 0, right? So again, we need to do the same thing, right? So I'm not even going to do, well, I'm not going to do it like that. Okay, so I'm going to be a bit cavalier, right? We have the start state, which is epsilon, and then we have the regular thingy. Okay, so we draw the same tree to remember the last 2 characters of the input, and now we just need to do, to fix it, right? To fix it in the sense that if we get 0, 1, 0, we accept, right? So for example, there's going to be an accept state, right? Which is this one, let's call it E for the end, right? And now this 0, this edge that was 0 is going to go here, right? So if we're in 0, 1, we get a 0, we go to accept because we saw 0, 1, 0. The heaven state, of course, if you get 0, 1, we stay there. And similarly, if we are at 0, 0 and we saw a 1, so this edge is gone, it's not relevant anymore. If we're in 0, 0 and we get a 1, we also go to the end, and that's it, right? That's the only 2 possibilities of getting to the end state. Either we get 0, 0 and then a 1, or we saw 0, 1 and then we get a 0. And that's it. That's the automata. Right. Yeah, and some situation it might be possible to draw a smaller automata with lower number of states. I don't immediately know if it's possible in this case. I don't think so, but I'm not sure. Okay, let's see another example. We want W, accept all W that have one K position from the end, right? So here we have to follow the same mechanism we did before, right? So the idea is that we're going to build a binary tree of states, right, as we did before, and this binary state is going to have height K. Right, so every state in the bottom, right, there are 2 to the k strings in the bottom of this tree, and now we put the transition between them in the natural way, right? You know, so that we always have this sliding window of k bits, and remember the last k bits we seen, and now we just mark all the states where the first bit in the string that encode them, you know, this is the kth bit, the last kth bit in the input is an accepting state. So you just go through them and you mark them. Half of the state will be marked, and that's it. That's the automata. You know, this is already a case where, you know, k is equal to 4 or 5. It's easier to in fact describe this formally. It will be slightly painful, but it's way easier than drawing this huge tree and all the transition, which, you know, is pretty mundane and boring, and one is bound to get it wrong. Okay, let's see even a more clever example. And here we want all the binary numbers that modulo 5 are equal to 0, right? Now, a priori, it's not even clear how to do that. But the important thing to remember is that if we have a binary string and we have a number and we add 0 to it, this is equivalent to multiplying the string by 2, right? And multiplying by 2 and computing modulo 5, if we care about the modulo, right? Now, this is really equivalent if the current value of the modulo of the string W is A. This is really equivalent to computing 2A modulo 5, right? And similarly, if we put a string 1, we are multiplying by 2 and we are adding a 1, right? So really, we need to move from whatever the current modulo is to 2A plus 1 modulo 5, right? So this is not difficult. It's just not going to be. So let's do it. Right. So how do we do it? Well, you know, as usual, right? We're going to have 5 states: 0, 1, 2, 3, 4, right? And now we just need to remember how the modulo behave, right? When you multiply it, right? So if I'm at 0 and I multiply it by 2, I remain where I am. So 0 keeps me where I am. If I get a 1, I go forward. If I get a 0, then effectively I'm multiplying the modulo by 2, so I go to 2. If I get a 1, I jump to 3, right? If I'm at 2 and I get a 0, then the modulo jump to 4, right? If I get a 1, then I have to go back to 0, right? It's like I multiply the modulo with 4 and then I add 1. Okay, so this was 3. 3, if I get 0, I multiply it by 2, so it's 6. 6 modulo 5 is of course 1. So I go back to 1. This is on a 0. Again, it's a mess, but hopefully you can follow the argument. And if I get a 1, then I go back to 2, right? Because it's 6, which is modulo 1, and I add 1. So this is 1. And now if I'm at 4 and I get 0, I multiply by 2, it's 8. 8 modulo 5 is 3. So I go back to 3. And if I get 1, then I get 8. you know, the modulo is 8, plus 1 is 9, 9 modulo 5 is 4, so I stay where I am. Okay, the only accepting state is 0. So that's what we get. It's, you know, the drawing is not great, but the solution is correct. And this is it.